Recording in progress.
This class is the last class for the summer calculus, okay? Here is the structures about the classes we have already finished in this summer. Limits, continuity, derivative rules, including chain rule, product rule, and quotient rule. And then we learned also about the logarithm derivative, tangent line equations. We also study about implicit method, inverse trigonometry derivative, extremes, okay, optimization, relative rates. And today we will learn the second derivative. For the extreme class, we know that we can do the candidates test to tell if the point can give us a minimum value or a maximum value. The 4 steps are listed here. Step 1, you want to look for your first derivative. And you make your first derivative to equals to 0. Or your first derivative does not exist. Based on these 2, you find your critical value, x equals to c. You may have multiple values of c. Maybe you have c1, c2, c3, several different values can satisfy your first derivative to be 0 or does not exist. Second step, you will calculate your f of c1, f of c2, f of c3. If you just have one of the value, you just do one of them. Third step, you will list a table to find your left bound and the right bound, okay? This is your lower bound, this is your upper bound. You find your f value, and then you check f of c1, f of c2, f of c3. You list the table, you compare them. And last step, you find the lowest value among them, and then you call that guy your minimum. You find the maximum among this table, you call it your maximum. This is using the candidates test without using the graphing calculator to find your minimum or maximum value. There are another method called second derivative, okay? We can use a second derivative to find the extrema also. So let's see here. If a function is differentiable on an open interval, if the graph is like this, if you have a curve like that, this is called concave up. This is concave up. That means you can hold this cup this direction. This is called concave up. Another way to tell if this guy is concave up, okay? If your first derivative is increasing. So simple function example. If you put y equals to x squared, y equals to x squared, this guy has a first derivative of 2x, okay? X squared first derivative is 2x. So this graph, the first derivative is like this, and this is y equals to 2x. Is this 2x, of course, it has a positive slope, so it is called increasing. So if your first derivative is increasing, or your second derivative is positive, you call this guy concave up. I say it one more time. If you found this function, second derivative positive on this interval, you call this graph concave up. If you calculate the first derivative, if the first derivative is increasing by using here or using here, you can call this function, original function, concave up. The other case, you have a fx equals to negative x squared. The first derivative equals to negative 2x. The second derivative equals to negative 2, okay? So this guy called concave down. You can use two different ways to tell this guy is concave down. Number one, you check your first derivative. This guy, first derivative is negative 2 times x to the power 2 minus 1, which is negative 2x. This guy is a line going down. This guy's slope is a line going down. So it's decreasing. Your first derivative is decreasing. Or your second derivative is negative. You call this guy concave down, okay? If you plan to take the College Board AP test in next May, this for sure will be included in the test, both for AB and BC. Okay, so we already introduced this. Second derivative positive in this interval. This function is called concave up in this interval. Second derivative negative in this interval. The graph is called concave down. Right. If you know how to speak and write Chinese, this is what it means, okay? This is a word called all, this is a word called to. So this guy is concave up, this guy is concave down, okay? Next one, inflection point. This guy has a lot of meanings, especially during the pandemic season, okay? So this is what happens like the pandemic, okay? We always care about what's the time for the inflection point, because right now, because last year it's going up like that. When we start to have those Pfizer's or other immunization shots, we feel like the inflection point will come. Then the people who get coronavirus will going down. But we don't expect that the Delta variant come and then another inflection point will come. So it's like this right now. Inflection point. Inflection point is very tricky, okay? Inflection point, you won't be able to see it by your eyes. You have to calculate by the math functions. This is a curve, okay? On this interval, is concaving up. This guy is concaving up. You hold your cup like this. This is called concave up. From this point, it is concave down, okay? This is a point called inflection point. Inflection point is calculated by making your second derivative equals to 0. We mentioned earlier, second derivative positive, concave up. Second derivative negative, concave down. This is the point changing from concaving up to concaving down. This is the inflection point, okay? So far, any questions? Okay, so this, if you find a point C and F double prime C is 0, or F double prime C does not exist, if on the left, your second derivative is positive, but on the right, your second derivative is negative, or on the left, the second derivative is negative, on the right, second derivative is positive, you call this inflection point. If you don't want to calculate the second derivative to be positive or negative, you can also check if your first derivative changing from increasing to decreasing or decreasing to increasing, okay? You can also, by using first derivative, increasing, decreasing to check if you are having this inflection point. Those concepts will not help you at all if and only if you work on the real questions. Let's see the first one. I'm going to hide my answers and I'm going to leave this there. Copy down the question, everybody. Copy down the fx. Go do the f prime x and f double prime x, okay? You can calculate it here. And then you do the derivative of the first derivative to give you f double prime. And then you want to check for which point your f double prime equals to 0. Angela, have you finished your f first prime and the second double prime?
Yeah.
Okay, go ahead. First derivative is who?
The first derivative is 4x cubed minus 12x squared.
Okay. Second derivative will be?
12x squared minus 24x.
Okay. As we mentioned over here, we want to make it equals to 0 to find the inflection points, correct?
Mm-hmm.
So we want to make this guy equals to 0. Then we found x equals to how much?
0 or 2.
Okay, so you found your x to be 0 or 2. But students, if you stop right here, if you don't move, if you don't write anything there, you stop here, you see, oh, at 0, at 2, that's the inflection point. You won't get the whole points. If this question is 10 points, you just get 1 point because satisfy this equals 0 does not guarantee you to be the inflection point. You have to check if your second derivative changes the sign or not, okay? So we need to move forward from over here. Let's look at here. Angela, look here. Second derivative equals to 12x squared minus 24x, which is 12 times x minus 2, correct?
Yeah.
And if x is negative, this is negative, yes?
Mm-hmm.
This is
Negative.
negative. Positive times a negative times another negative is
Positive.
positive, okay? So this is positive. Next, we want to move to the right of the 0, okay? Yeah, we know that on the left here, on the left of 0, your second derivative is positive. Now we want to check on the right, is this guy negative or positive? Let's see. 12 is positive, yes?
Mm-hmm.
The next is between 0 and 2. x is positive, correct?
Yeah.
When x is less than 2, x minus 2 is negative, correct?
Mm-hmm.
So positive times a positive times a negative go to a negative, yes?
Yeah.
So here is negative. Next, when we move to the right of positive 2, when x is bigger than 2, let's check the double prime, okay? The 12 is positive. X is bigger than 2, of course, x is positive. X minus 2 is
Positive.
positive. So all the product is positive, correct?
Yeah.
Now, we have this sign chart. This is our double prime sign chart. You have a 0, you have a 2. On the left of 0, this is positive. Between 0 and 2, this is negative. At the right of positive 2, it is positive. So second derivative positive, this is concaving up, right?
Yeah.
This is concaving up. This is concaving down. And this guy is concaving up. That means your second derivative is changing sign on these two critical points. So what does that mean? These two are the correct inflection point. Make sense?
Yeah.
If we want to see this, okay, if we want to see this in the graph calculator, now you can do x to the power of 4 minus 4x to the power of 3, okay, and you have this curve. So that means you look at here, the first point is at x equals to 0. You can put x equals to 0. When x is 0, y is also 0, okay? You see this point. You see on the left of this point, the cup is concaving up. On the right of this blue point, the cup is concaving down, right?
Yeah.
You see here, there is concaving up, there is concaving down. So this agrees with what we calculated, okay? This point, we can easily see this inflection point by our eyes. But the other one, this guy, is not easy to find it. When x equals to 2, let's calculate. When x equals to 2, f of 2 equals how much? This equals how much? Negative 2 to the power 4, right? Negative 16, correct?
Yeah.
So 2 comma negative 16. This guy, believe or not, this is another inflection point, okay? This is another inflection point. You won't be able to see it by your eyes, but you can calculate this, okay? You can calculate this. You see that point over here. On the left of this point, this guy is a concaving down. Right from this point, your curve becomes concaving up. So this is the first inflection point. This is the second inflection point, okay? So you might wonder why I cannot just say, as long as I find this equals 0, and then I'm able to tell that's the inflection point. Let's see here. There is another way to tell your inflection point. You can use your double prime and then check your second derivative, positive or negative, on the left and on the right of your value, okay? Or you can use your first derivative to check. Who is the first derivative for this one? Angela, who is the first derivative?
4x cubed minus 12x squared.
4x cubed minus 12x squared. 4x cubed minus 12x squared. So we can draw this guy on the graph calculator. So this is the first derivative. This is first derivative. The definition over here for the inflection point saying if you are changing from increasing to decreasing, see here, it's changing from increasing to decreasing. And you are changing from decreasing to increasing, okay? As long as your first derivative changing from increasing to decreasing on this point, this is an inflection point. From here to here at x equals 2, this curve, your first derivative, is changing from decreasing to increasing, okay? So this is also the inflection point. So question come to here. Why I cannot just do this? Use this one to say, hey, as long as I find this equals 0, I can tell this is my inflection point. I give you a counter example, okay? So for example, we can just find a very easy one. Y equals to x to the power 4. Angela, let's do this guy's first derivative and then second derivative. Go ahead, please.
First derivative is 4x cubed.
Second derivative
is 12x squared.
Okay. So if you say, I'm going to just make my second derivative equals to 0, okay? That means 12x squared equals to 0. So x equals 0, right?
Yeah.
Yeah. And if we say, well, we already see this guy equals 0. And then I'm going to say x equals 0 is the inflection point. I tell you, this is wrong. Why? Let's take a look. Your first derivative, your original one is x to the power of 4. Okay, yes. Look at this. At this position, your graph is always curving up. It is not changing from curving up to curving down or concaving down to concaving up. This point, by no way, that can be called as an inflection point, right? Because we can check. Look, if you want to claim this point is the inflection point, you should not miss the other part by checking your second derivative changing sign or not. So we can do here, we do the sign chart. This is x equals to 0. Your second derivative is 12x squared. Look at this. On the left, when x is negative, is this positive?
Yeah.
Negative square is positive. On the right here, your second derivative is also positive, correct?
Yes.
Right. Positive change to positive. No, this is not called a change. It keeps the same. The sign does not change. X equals to 0 is not the inflection point. Does this make sense?
Yeah.
We can also check if you don't like using second derivative sign chart to tell if the sign change or not. You can also run the first derivative. The first derivative is 4x cubed, okay? 4x cubed. So 4x cubed, this guy. This curve, look, this curve on the left and on the right. On the left of 0, it is increasing. On the right, it is also increasing. Okay? It is increasing. So it is not changing the direction. Not like here. Here, increasing, decreasing. So this can be claimed as an inflection point. This one, decreasing, increasing. So this can be claimed as an inflection point. But that example here, on the left increasing, on the right increasing, there's no way you can call this guy inflection point. So you can use the second derivative way. This is not an inflection point. Or you can check the first derivative. Increasing. Again, x equals 0 is not the inflection point. Does this make sense now?
Yeah.
Okay, students, most students just remember this step by doing, say, that's easy. I do the first derivative, do the second derivative, make it equal 0, find the x value, and then call this guy as an inflection point. If you only do this part, you just finish 20% of the question, okay? You have to run here, or you have to run here to tell. Next, we can use the second derivative test to help us find the minimum or maximum. I have already mentioned this during the candidates test, okay? So you can run the first derivative equals 0, and then you run your second derivative at this location. If this is positive, this is concaving up. This point is a minimum point. You run the first derivative equals 0, and you check your second derivative at this point. If it's negative, then this is a maximum. It's concaving down. Now let's do the practice. Okay, everybody, you can go ahead, start this question. I already put the structure over here. You find your first derivative, and you find your second derivative, and you make your first derivative equal 0, and then you put that value into your second derivative to check. Everybody can go ahead. Cindy, you finished?
Not yet.
Finished? Let's do this together, okay? Cindy, can you tell me your solution for here?
So negative 15 x to the power of 4 plus 15 x squared.
Okay. What do we do next?
So next you find the second derivative, which is negative 60 x cubed plus 30x.
Okay. We want to find the relative extrema. So we want to make which one to be 0?
We want one of this. We want f double prime.
No, hold on. Don't be confused between the inflection point and the critical point, okay? For the extrema, you're looking for your first derivative to be 0. And then you plug in the C value into the second derivative to tell if it's concaving up or concaving down. For doing the inflection point, you are checking your second derivative to be 0. And then you check if your second derivative is changing from positive to negative or from negative to positive at the position of the inflection point. So don't be confused with this. This question, we are checking this function is concaving up or concaving down by finding the inflection point first. So we make the second derivative to be 0. And then we check the sign, positive or negative, of the second derivative function. But when we come back to the extrema, which means the minimum or maximum, we are checking the first derivative to be equals to 0 and find those critical points. Okay? So we want to make this guy to be 0. Is this clear?
Yes.
So make this guy to be 0. Let's solve this one.
So you just take out negative 15 x squared, and then you can factor out the x squared minus 1.
So x equals?
So x equals negative 1, 0, and 1.
Negative 1, positive 1, or 0, correct?
Yes.
Okay, so we have 3 critical values, okay? These are called the three critical values. And then we want to use the second derivative to help us check if it's a minimum or maximum quickly, rather than doing the candidate's test. Okay? So we will plug in here, there, and there. Okay? We plug in here. Let's see how much is this guy.
30.
This is the positive 60 minus 30, which is 30, right? Right. Bigger than 0, yes?
Yes.
If second derivative is bigger than 0, it's concaving up. So that point is the minimum, right? Minimum at x equals to -1. Let's check how much is this one.
This one is just 0.
Oh, this one is 0. We don't know if the second derivative is 0. We cannot see this is a mean or this is max. We don't know. We might be able to tell if this is an inflection point or not. Okay? This second derivative equals 0 does not tell you if you get the mean or max. Second derivative go to 0 may tell you this point might be the inflection point. Depends on the left, on the right. Does this guy change sign? Does this make sense?
Yes.
F double prime of 1 equals
-60 plus 30. So -30.
You mean -30, right?
Yeah.
Okay. This is less than 0, so it's concaving up. That is the maximum point. Does that make sense?
Yes.
Okay. And this question does not ask us for the inflection point, but we are just curious. We want to see, is this point an inflection point or not? So we can do the extra step, okay? This step is not required to answer this question, but we are just like a curious judge. We want to see, okay? When x is less than 0, look, when x is less than 0, your double prime is bigger than 0, correct?
Yes.
When x is bigger than 0, your double prime is less than 0. So your second derivative change the sign at the position of this. So the x equals 0 is called the inflection point. Make sense? Okay. So we still want to see the graph, okay? We are just like a curious judge. We want to see. Okay, oh, this is the graph like that. You might say, why cannot use candidate's test? Look, candidate's test needs you to have an interval. This one does not tell you the interval. You won't be able to do the candidate's test. Candidate test, you have to have the lower bound and upper bound and run the table. This one, they didn't tell you any lower bound or upper bound. You are not able to find the extreme values. So you can only use the second derivative to find the extrema here. Okay, so there at x equals to -1, at this point, your second derivative is bigger than 0, concaving up. So this gave you the minimum point, local minimum point, or relative minimum point. On this position, your second derivative is less than 0. So it is concaving down. It's concaving down, and this point is your maximum point. Okay. Okay. So go ahead, finish your notes. Please ask me question. Okay. Please ask me question if you feel confused at any place.
Wait, teacher.
Mhm.
So like the final answer, like the relative extrema are just like it doesn't include 0.
Sorry, can you repeat your question one more time?
Like the final answer, like so you're supposed to find the
You don't need to have here. Everything exclude this part is good enough for this question. You don't need to write down. This question does not ask you for the inflection point. Okay.
thank you.
Now, if they put the question into 2 parts, they say A, find the relative extrema. B, find your inflection point. Then you have this, okay? So far, so good. Now we are going to do a hard one, okay? Yeah. Next question might be trouble for most students. First, go ahead, see if you can do this by yourself. Critical values, extremes, candidates, test, second derivative, inflection points. All of these are 100% sure included in the AP test, either A, B, or BC, okay? Those topics are for sure in those tests. Lawrence.
Yes.
Let's see this question. Go ahead, read it, please.
Suppose a function f has continuous second derivative for all x and that f of 1 equals -3. The derivative of f of 1 equals 5, and then the second derivative of, or f of 1 second derivative is -4. Let g be a function whose derivative is given by gx derivative. It's going to equal the x cubed plus 1 at times 5f of x plus 3 derivative of 3x prime for all
F prime x.
f prime x for all x. Does g have a local maximum or a local minimum at x equals 1? And then justify your answer.
Yeah, this question sounds very complicated. So here, they give us the G prime expression. This is G prime, okay?
Okay.
If they want you to find a local max or local mean, so we go back here. You want to find your local max or local mean. You want to find your first derivative go to 0. This question is not asking you for your inflection point. If they ask you for the inflection points, of course, you do the second derivative and make it equals 0 and find your x. But this question is asking you for the local mean or local max. So they ask you get the first derivative and make it equal 0. Does this make sense?
Yes, that definitely makes
sense. So this is cleared, okay?
Yeah.
Students, if my question is asking you for inflection points, you go ahead, do the double prime and make that guy equals to 0. And then check if your double prime is changing sign on the left or on the right. If my question is asking you for local max or local mean, please don't make your double prime equal 0. Make your first prime equal 0, just like what you learned in the previous class about the candidate's test. You find your first derivative equals 0. That's the first step to help you find your local mean or local max. Is this clear?
Mm-hmm.
You make this guy equal 0. If you make this guy equal 0, what do you find? You want this to be 0. So
don't we have to like solve that?
Yeah.
We have to simplify it.
This equals 0, so?
All of that equals, and then x or this must be an x cubed must equal -1. Just -1, yeah. Mm-hmm.
Oh, this is 0, right?
Yeah, or that is 0.
Let's make that guy to be 0.
Okay.
But they look. But they are nice. They told us your x equals 1, right?
Excellent, yeah.
So yeah, so we can check. F1 is how much?
F1, they already gave it -3.
F1 -3. F prime 1 is how much?
It's 5, as they give.
5. So 5 times -3 plus 3 times 5, correct?
3 times 5, right.
Equals?
And it cancels them out, so it would be 0.
That's right.
Okay.
So that means x equals to 1. Maybe a local minimum or local maximum because the first derivative is 0. Okay?
Okay.
Now we want to plug in this x equals to 1 into the double prime. Okay?
Equal double
we want
prime.
to make we want to check if this is positive or negative. So the question comes to how do we find this guy's derivative?
We have to do everything derivative.
Yes.
Entire expression.
Yes. So look at here. This question is not hard except getting this piece. Okay. We want to do this guy's derivative. We want to use product rule. Okay.
Product rule. Okay.
So go ahead.
So first we can just solve for the derivative of the first part, so it'll be 3x squared. I think.
Yes.
Yeah, 3x squared. And then we can copy everything down.
Yes.
From the other expressions. And then we can add that to, we copy the first expression down, x cubed plus 1. And we do derivative of that, so wouldn't it, is it 5?
You have to do
you have to do
x.
Okay, you just add, okay. And then it'll be plus 3x and the f double prime, then I think.
That, yes. There
Okay.
you go. So far, so good.
So far, so good. Yes.
Okay. This guy derivative copy down. This guy derivative over here.
Yes.
This guy exactly copy down.
Exactly.
This
Right.
guy exactly copy down. This guy derivative.
Mhm.
So phi is a coefficient. Just copy down. This guy derivative is f prime x.
Yeah.
3 copy down. This guy derivative becomes to f double prime. Okay.
Okay. Okay.
All right. So this is the guy.
All right.
Now we want to check when x equals to 1, how much is this value? Okay.
Okay. That shouldn't be
Now
too.
I'm going to erase this part and let's do it together.
Okay.
3 times.
It'll be 3 times. And then I think didn't we get this before? Was it 0 before?
3 times 1 is 3. Okay. Yeah.
Oh,
X
yeah,
equals
then
1. X times 1 squared. So, and then times 5.
5, yeah.
F1 is how much?
F1 is just -3 times -3.
Okay.
And
Plus
then plus 3 times 5.
3 times 5. And then
we
plus
can add. And then since it's just 1 cubed is just 1 plus 1 is 2. Times 5 times, we know that's just 5. 5 or f prime is just 5, I think. And then we can add 3 times, and we already know f double prime of 1 is just -4.
F
3
double
times,
1 is -4.
yeah, 3 times -4. Yeah.
Okay. All right. Now this is -15.
Yeah.
And this is plus 15.
Yeah.
So this becomes to 0.
This becomes 0. And we can.
This is 0. So this is 5 times 5 minus 12. Okay.
Minus 12. Okay.
This is gone.
Yeah.
This is 2 times 25 minus 12. So 2 times 13. That's 26. Correct.
26.
There you go.
Okay.
Because here is positive, so it has a local minimum at x equals to 1.
Okay.
Makes sense?
Yeah, it makes sense.
Oh, this question looks very complicated. And this is those similar AP free response question. Okay. As long as you know the procedure, it is not hard at all.
Yeah.
Okay. Any other question here? Other students? Is there any questions? No question? Okay. If no question, we move on to the next one. Let's see example here. They ask us to determine whether where the relative max or relative minimum occurs if they exist. So we want to do this one. Okay. Go ahead, everybody. Get the first derivative and solve it to be 0. Okay. Do this one. Use the same way as what we did earlier. Okay. Claire, let's do this one together. Go ahead, tell me what's the first derivative.
3x squared plus 7x plus 2.
Okay. We want to make this guy equals to who?
0.
Okay. How do we factor in this one?
That would be 3x, or open parentheses 3x plus 1 close parentheses, and then open parentheses x plus 2.
Okay. So the x will equals,
Negative 1/3 and negative 2.
okay. What's the second derivative?
6x plus 7.
Okay. Now let's put -2 into here to check, okay?
Okay,
Mhm.
sorry, that's negative 12 plus 7, which is negative 5.
Less than 0.
Yes.
This will be concaving up or concaving down?
Down.
Concave down. So that's the local minimum or local maximum?
Local.
Maximum, right?
Yeah.
So this is your corresponding local maximum. And let's do the other one. F double prime of -1/3 equals?
So that'd be negative 2 plus 7, which is 5.
2 plus 7, which is positive 5. Concave up, okay?
Mhm.
Minimum, right? Oh, that's it. Okay. Now the second one. The next question is a little bit challenge, okay? Not too bad. Just depends on how well we mastered everything we have learned before. Olivia. Let's go ahead to the next one.
Okay.
F prime u equals?
Okay, so it's 1/2 times x squared plus 1 to the -1/2 power. And then times 2x. And then, yeah, minus 2x.
Correct. And this 2 and 2 canceled, so we can rewrite this as x over
X over square root of x squared plus 1.
okay. And then minus 2x, correct?
Yes.
Okay. And we want to make this equals to 0, correct?
Yes.
Okay. And let's solve this one equals to 0. Okay, let's solve this one equals to 0. If we want this guy to be 0, then x will equals to who?
X equals 0.
Or, or this guy equals to 2, correct?
Yeah.
And then this guy will equals to 1/2, correct?
Yes.
That means x squared plus 1 will equals to how much?
1/4.
1/4. X squared will equals -3/4. That's impossible, okay? And no real solution. And we don't talk about the imaginary solution over here. No real solution, okay? Okay. And then we want to do the second derivative. We want to do this guy's derivative, okay? Let's go ahead and run this guy derivative using the quotient rule, okay?
Okay. So it's 1 times square root of x squared plus 1.
Top one derivative is 1 times the denominator minus
X
times
times 1/2 times x squared plus 1 to the negative 1/2 times 2x.
very good.
And then the denominator would be x squared plus 1.
That's right. Let me see this one more time, okay? We want to do the first derivative so that we can get the f double prime x. This guy derivative, using the quotient rule, top one derivative is 1 times the bottom one, copy down, that, minus the top one, copy down, the bottom one derivative, which is 1/2 times this guy to the power of 1/2 minus 1 is -1/2. And then times this guy derivative, which is 2x. Okay, very good. Minus this guy derivative, how much?
2.
Minus 2. Okay, there we go. And then we can simplify this, okay? 2 and 2 will cancel. This 2 and 2 will cancel. And this becomes 2x squared, okay? All right. And we want to check at the position of x equals 0, how much does this second derivative equals, okay? Let's go ahead. 0 put here, how much?
1.
Okay. This is 1 minus, this can be ignored because 0 times everything is 0, right?
Yes.
Denominator is
It's 1.
1. And then minus,
Minus 2.
okay, equals
-1.
-1, less than 0. It is concaving up or concaving down?
Down.
Concaving down. Concaving down, and this value should be the maximum, right?
Yeah.
Okay, and we want to find out when x equals 0, y is how much? So we plug in. We can plug in. When x is 0, y will equals to square root of 0 plus 1, and then minus 0. This equals to 1, correct?
Yeah.
Okay. So we can tell calculus is a really powerful tool because previously, without learning calculus, we have to use calculator to draw this one. And this is definitely a complicated graph, okay? And if you want to tell your minimum or maximum, now you can just using your calculus way to tell this point without graphing, and it's the same answer, okay? So far, so good. Okay. Next one. We want to be able to tell, okay, determine the function. When does it change the concavity? So let's see here, first one. I show the first one example and then I call students, okay? Your original function, you can change this. This is, look, this is x squared and then minus 5x plus 3x. So this is negative 2x and then minus 15. And your f prime, you go to first derivative, you go to 2x and then minus 2, okay? Your second derivative, this guy is 2. This guy is 2. You don't have any variable anymore. So this function is concaving up on all the intervals, on all the negative infinity to positive infinity. So this guy is always concave up. And as a matter of fact, you know this guy is a parabola opening up, okay? So of course this guy is a concaving up. So for those polynomials, second derivative, second order, like parabola, opening up, that's concave up. Opening down is concaving down. But the question will not be so simple when you come to the polynomial of third degree or fourth degree, okay? When you have trigonometry involved, it's going to be more complicated. Now let's do the second one. Joy, let's do the next one.
So for the first derivative, it would be 3x squared plus 6x plus 3.
Okay.
And then the second derivative is 6x plus 6. And then
we want to see at what location it is concaving up. Okay, so if we can check, we can solve this inequality. X will be bigger than.
yeah, so you'll have -1.
6x bigger than negative 6x is bigger than -1. Okay.
Yeah.
And because when x is bigger than -1, this is bigger than 0. Second derivative bigger than 0. So concave up. Okay. Yeah. We want to find this guy less than 0. Go ahead.
Yeah. And that's also -1.
But less than. Concave down. Okay.
Yeah.
And we can even tell f prime of -1 equals 0. Yes. And this guy, we can draw the sun chart. We can know that f double prime x on the left, it is positive. On the right, is negative. At this point, it's 0. So x is
An
negative 1
inflection.
is the inflection point. Exactly.
Yeah.
They didn't ask this question, but in case they ask, we can do it. Okay.
Mm-hmm.
This is the inflection point. And there, your double prime is always positive. So you don't have any inflection point at all. Okay.
Yeah.
That makes sense. Thank you. Next one. Number 3. We have polynomial with trigonometry together. Zhao Yuchen, let's do number 3. How much is f prime x?
Change to cosine
Mhm.
to cosine 2x plus 2x.
Sine 2x derivative is cosine 2x. And then we need to times 2, correct? So this guy times 2 plus,
2x.
very good. Now let's do the second derivative.
Negative 4 sine 2x.
Okay, very good. Cosine 2x derivative is negative sine 2x. This guy is using the chain rule, so we have to times another 2. And then times this 2, so that's times 4, right?
Yeah.
Hey, very good. That's good.
And
This guy go to this and go 4. This guy derivative is
plus 2.
plus 2. Make sense?
Yeah.
So we want to find the extrema, right? No, we want to make the first derivative equals to 0, correct? Oh, they are, okay, don't worry, we don't need to get the extrema, we just check the concavity. So we make this guy, check this guy bigger than 0 or less than 0, okay?
Oh, okay.
We want to, they didn't ask us for minimum, maximum, they asked for concavity, so we only care about the second derivative. So we want to check this one, okay?
Okay.
Yeah, we want to say for sine 2x negative plus 2. And we want to first make it equal 0, okay? Yeah, let's solve this one. So sine 2x equals
1 over 2.
positive 1 over 2.
Okay.
The interval they give us is from 0 to 2 pi. On this interval, who gave you sine 2x equals to 1/2?
I'm sorry?
Sine 2x equals 1/2. 2x should equals to how much?
Pi over 6.
Yes. 2x might equals to pi over 6. Who else?
5 pi over 6.
Yes, very good. Okay. So if okay, let me put this one over here. Look, when 2x equals to pi over 6, x will equals to how much?
Pi over 12.
Pi over 12. When 2x is 5 pi over 6, x equals
5 pi over 12.
5 pi over 12. I think when I teach you the trigonometry equations, we mentioned something about if there is a 2, you have to add in another 2 pi. Kind of remember? Because if we add another 2 pi after divided by 2, our x will still fall in this interval. So we want to add another pi, a 2 pi. This guy plus 2 pi is same as 12 pi over 6, right? So that's how much? 13 pi over 6. Make sense?
Okay.
This guy plus 2 pi, which is 12 pi over 6, which equals 17 pi, right?
17 pi, yeah.
17 pi over 6. And then divided by 2. Makes sense?
Okay.
Look, if I don't have a 2x, if I just have an x, then your x equals to pi over 6, 5 pi over 6. That's all. Because you have a 2 over here. If you have 2 over here, you will not just have 2 solutions, you will have double of this. Okay?
Okay.
If you have 3 here, you will have 1 pair, 2 pair, 3 pair. If you have 4, you have 1 pair, 2 pair, 3 pair, 4 pair. Okay? Yeah. So x will equals to this 4 different values, and all of this belong to this interval. Correct? Okay. So now we have these 4 values, and we want to see on what part the double prime will be negative and on what part is going to be positive. Okay. So we are going to draw the sun chart. So we start from 0, and then we put pi over 12, 5 pi over 12. And this is 2 pi, okay? 2 pi equals to 24 pi over 12. So look at here. If you have a value lower than pi over 12, your sign, if your x is less than pi over 12, then 2x will be less than pi over 6, correct?
Yeah.
And then sine pi over 6 will be less than 1/2, correct? If this guy is less than 1/2, then this guy will be positive. Do you agree?
Yeah.
So this is plus.
Okay.
But if you are beyond this point, then your sine pi over 6, this guy, if your 2x is bigger than pi over 12, I mean, if your x is bigger than pi over 12, 2x will be bigger than pi over 6. Sine 2x will be bigger than 1/2, correct?
Yeah.
Now, if this guy is bigger than 1/2, then this will be
Down.
make this less than 0, correct?
Okay.
Make sense? So this is negative, okay? And then let's see over here. When your x is going to go beyond this point, it's going to be if x is bigger than 5 pi over 12, then your 2x will be bigger than 5 pi over 6. So you know that you have this circle. if your angle was pushed below this point, your y value will be less than 1/2. If that's less than 1/2, then this guy will be positive again. That makes sense?
Mm-hmm.
Okay, that's positive. And you can see here, okay, you can see here, if x is bigger than 13 pi over 12, then 2x will be bigger than 13 pi over 6, okay?
Mm-hmm.
Bigger than 13 pi over 6, what does that mean? That means 13 pi over 6 is 2 pi plus pi over 6, okay?
Mm-hmm.
So we'll be above here. So your sine 2x is bigger than 1/2 again, okay?
Okay.
Yeah, then that guy will becomes to negative.
Negative.
Make sense? So your sun chart is like that.
Okay.
Okay, now everybody take your time writing down the notes. Okay. Students, this is my calculus class. If you are not belonging to this class, please come back until 3:05, please. Now you can tell calculus itself, the concepts are already very complicated. When they have those trigonometries, okay, unit circles, double angles, inequalities involved, it becomes way more complicated. So everything depends on how good your foundation is. Okay, so this is concaving up, concaving down, concaving up, concaving down, concaving up. Okay. Okay, that's for number 3. For number 4, your function is this. This is your given function. If you want to do this guy derivative, okay, if you use the quotient rule, definitely you can do it. Yeah, if you do the f prime of x, if you do the f prime x, you will do this derivative times this guy copy down minus this guy copy down times this guy derivative. It's really ugly, okay? It's really long. So I like to do something shortcut. Look at here. This guy, I change it. X squared minus 1 is x squared plus 1 minus 2. This is 1. This is this. 1 minus here. Okay. So I rewrite this complicated function into this simple version. And then I do the f prime. Constant derivative is 0. This guy, power rule and chain rule. I tell you, power rule, chain rule is way more better than quotient rule. Quotient rule is really ugly. In this way, I change this to a power rule and chain rule. Becomes an easy question. And I find my first derivative. Because I'm checking concaving down or concaving up, so I need to find the second derivative for this guy. I can do this guy derivative. And I'm able to reach to here. Simplify this, coming to this. This top and this one can cancel. So x squared plus 1 was left. This becomes the 1 minus 3x squared. You want to check your concavity. So you want to make this bigger than 0 or less than 0, okay? And then you find out when x is bigger than square root 3 over 3 or less than negative square root 3 over 3, it's concaving down. When it is between, it is concaving up. Okay. The graph of this one is this guy. Okay. So on the left of this purple line, this guy is concaving down. Between here is concaving up. Beyond this green point, it's concaving down again. Okay. I upload both the blank worksheet and the solutions, okay, with all my notes. This is the last class for the summer calculus class, okay? When school starts, I haven't decided the final class time yet because we have students from the places with New York time. We have students from Houston time. It's hard for me to find a time which make everybody happy. I'm still checking schedule, okay? Yeah, you can, if you want to continue with my class, let your parents contact me in the WeChat, okay? Thanks for taking my class in the summer. Wish you a successful school year, okay? Bye-bye.